Hi everyone, welcome to another video for research design and analysis. In today's video we're going to be talking about the dependent samples t-test, which is going to be our first in a series of videos where we talk about models where we're dealing with repeated measures. So let's create a hypothetical situation to kind of orient ourselves to what we mean by repeated measures. So let's pretend that I've created a diagnostic test of medical decision making, and on average people score about 500 points on this test. If someone scores over 600 points, then they're showing like exceptional diagnostic and medical reasoning. To the right are data from 10 subjects who took this, fictitious medical reasoning test that I made up. And we're going to be recording data from 10 people at two different time points. The first is condition number 1, where they take the test prior to being fatigued from working a 12-hour shift. And the second is condition 2, where they take that test again immediately at the end of their 12-hour shift. So the idea is that we've induced fatigue between these two time points. So we have one unfatigued condition and one fatigued condition. And we want to see, did medical reasoning change as a function of the fatigue? Well, if we plot these data, right, so we've got unfatigued as the green and the fatigued data points as the red, you can see that we actually have 2 data points for each individual. So this is going to violate the assumptions of our previous statistical tests where we said we need independent and identically distributed data. These data are not independent because I have 2 data points for each person. And as you can see, data from the same individual are more like each other than they are different, right? So high scoring people, even when they're fatigued, right, tend to be high scoring people. Low scoring people, even when they're fatigued, tend to be low scoring people. So knowing something about one observation tells me something about the other observation. So that is statistical dependence that is induced by the fact that I have repeated measurements from the same individuals. So we're going to look at this kind of the wrong way first, because it would be a mistake to analyze this using an independent samples t-test. But oftentimes, if people just think about, oh, well, I have 2 different conditions, I know how to do a regression model with a categorical predictor that has 2 levels, I'll do an independent samples t-test. But that's actually going to be the wrong thing to do. But the key question will be, why is that the wrong thing to do? So let's proceed with analyzing the data, though, as if these were an independent samples t-test. We'd calculate the mean of the unfatigued condition, which is 540.5, the mean of the fatigued condition, which is 530.2, right? And what we would be asking then is, are these 2 means statistically different from each other? So in order to calculate this, right, we would need to get some estimate of the mean difference, which we now have, and then we would divide that by the standard deviation, or sorry, I should say the standard error of the means. So in our independent samples t-test, that would look like this, right? We're going to calculate a t observed, where we're taking the difference between the 2 sample means, and we're dividing that by the standard error of the differences. And so what we're asking, right, with the t statistic is the difference between our sample means unusually large given the variability that we would expect due to sampling? And if we actually carry this all the way forward to do an independent samples t-test, this would be the mean in the fatigue condition. This is the mean in the unfatigued condition. These are the 95% confidence intervals based on the 10 subjects that we have in each of those conditions. We get a mean difference of 10.3 points, but we see that that difference is not statistically significant. The t observed was only negative 0.57, and the p-value for 18 degrees of freedom is 0.575. So there's no evidence really for a difference here, right? We can't really reject the null in this situation, even though our mean difference was pretty large, because our variability is so large, right? It's not unusual to get a mean difference of 10.3 here because the data are so very variable. So what do we conclude in this situation? Well, admittedly, we've run the wrong test, right? But based on the data and the statistical methods we used, we did not find evidence that fatigue has an effect on medical decision making. But, right, as we said at the beginning of this, there is a problem with the way we've analyzed the data in that study, right? We were analyzing things that are statistically dependent as if they were independent, and this is going to create a problem. We can't use an independent samples t-test in this situation because it's going to lead us to the wrong answer. To understand a bit more about why this is going to lead us to the wrong answer, let's consider what being statistically dependent really means. Well, remember that condition 1, right, and condition 2 are the same people being tested at different times, right? So they have a pretest, they have a post-test. We're looking at their medical decision making in both of those times, and in the middle of that, they're working a very fatiguing 12-hour shift. Now, there are multiple sources of variability here that are influencing the scores that we observe at each Now, there are multiple sources of variability here that affect the scores that we observed. One thing is the effect of fatigue, and fatigue affects the change we're seeing between these two time points. Other sources of variability are, gender differences, handedness differences, age differences, experience differences, training. Was one person having just a bad day to start with? Was one person already emotionally strung out at the start of the test? Right? All of those things are going to contribute to individual differences. So our effect of fatigue exists within a person, but all these other things are creating variability between people. So what we would really like to do is exclude or in some way account for the variability between people in order to get a cleaner assessment of the actual effect of our intervention, or in this case, the fatigue condition. So these large individual differences are part of what's going to make scores from the same person more like each other than they are like other scores, right? Like we said, someone who has a high score at the pretest is also likely to have a high score at the post-test. That would be positive statistical dependence because there's a positive correlation between these repeated measures. So repeated measures from the same subject are going to cause a problem because they're statistically dependent on each other. And this then confounds what we're trying to understand when we look at the effect of our intervention, which doesn't occur between people, it occurs within people. So to understand what variance in the dependent variable is actually explained by the independent variable, we're going to need to control for this dependence and essentially say, not were you a high or low score, but were you a high score relative to yourself, right? Accounting for what kind of person you are. Did you score high in this condition or did you score low in this condition? So let's think about our basic formula for hypothesis testing, right? Where we think about the variance explained by the independent variable being divided by the residual variance that remains unexplained. Whether it's t-tests or f-statistics, this is what we are essentially looking at as ratios for those inferential statistical tests. The bottom part of the equation, this unexplained variance, is actually composed of many different parts, and it's important that we have the correct denominator in order to make sure we're asking the right question. This can change and this variance can increase due to things like measurement error, due to individual differences, due to other factors, right? And we need to make sure we are properly accounting for all of those things in our statistical model in order to make sure we're calculating this ratio correctly. So in this instance, when we have repeated measures from the same person, one of the things we need to then account for is that we have data coming from the same people. So we'd like to pull that part out and remove it. And then we can look at the variance explained by the independent variable relative to the residual variance after we've accounted for which person you are. So when we think about removing these individual differences, I think it's helpful to visualize this with an illustration. So let's think about, again, the green is the pre-fatigue condition, the red is the post-fatigue condition. You can see that now we've got differences due to time, right? Differences between the red and the green shapes. But we also have differences due to person, with some people scoring higher, some people scoring lower at the start of the experiment. It has nothing to do with our intervention. So what we would really like to do is remove those individual differences. And essentially by making everyone's pretest kind of the reference condition, right? We can now say, well, did you tend to decline or did you tend to increase relative to that pretest condition? And then by looking at those differences, we're going to have independent data that we can actually analyze using a dependent samples t-test. So to calculate this dependent samples t-test, the first step would be to calculate the actual statistical dependence in our data with a correlation. So we have people's pretest scores, we have people's post-test scores, and if we calculate a correlation for those 10 scores, we find it's a very strong positive correlation. So people who tended to score high on the pretest also tend to score high on the post-test, confirming what we saw visually in the data. Next, instead of comparing the difference between means, right, for the mean of the pretest and the mean of the post-test, we need to remove the variability due to which person you are, and we can do that by calculating difference scores. So we can take the difference between pre-test and post-test. In this case, they scored 37 points lower on the post-test. This person scored 20 points lower. This person actually scored 1 point higher, right? But we'll now have 10 different scores. And we now have 10 independent observations because I don't actually have any data about, okay, if this was a low score, is the next person's score going to be low or high? Because I only have one observation per person, and these people are, don't have any kind of fundamental relationship to each other. I have independent data in this situation, and now I can analyze those different scores and calculate the appropriate t-statistic, where I can look at the average difference, right, relative to the hypothesized difference under the null hypothesis, and then divide that by the standard error of the difference. So by computing the appropriate t-statistic, right, using a dependent samples t-test, what we're actually going to see here is that there's a significant effect of fatigue where we have a t with 9 degrees of freedom of negative 2.41 and a p of 0.03. So if we compare these two things side by side, it's important to notice what's the same and what's different in these two situations. Right? When we looked at our independent samples t-test, which is the incorrect approach, the mean difference was negative 10.3. Now, when we look at our dependent samples t-test, which is the correct approach, the mean difference is still negative 10.3. So in both of these analyses, right, that mean difference remains the same. Up here, we calculated the mean in each condition and then took the difference between the means. Down here, we calculated the differences first and then took the mean difference, but mathematically those things are equivalent, so it's still a mean difference of 10.3. What changes, though, is the standard error of that difference, because when we're using the independent samples t-test incorrectly, we're lumping all of that variability due to which person you are into the standard deviation, and that in turn inflates the standard error. When we're calculating it as a dependent samples t-test, correctly, we are looking at each person relative to themselves. So we are controlling for which person you are, right? We've removed that variability from the model. And then we're saying, okay, did you just tend to have a positive or a negative difference between these two conditions? And you can see that the standard error then gets a lot smaller. It goes from 18.02 to 4.27. If I take the ratio of those mean differences then, right up here, our mean difference was only about half of the standard error. Down here, the mean difference was about 2.5 times the standard error. And so by analyzing these data correctly and recognizing that we have data coming from within the same person over time, we actually have a much more powerful statistical test